Okay, so we are on the 5th video of the series. We are starting on chapter 2 on capacitors. In this first video, I want to talk about just a single capacitor. I'm not going to combine it with other capacitors yet. Okay, so let's get started. We can read the question actually. It says a capacitor stores 80 microcoulomb. So I'm just going to write down there, charge is 80 microcoulomb when they are connected to a potential difference of 16 volts. So V equals to 16 volts. Determine the capacitance of the capacitor. Okay, so in order for me to calculate that, I have to remind myself that Q is equals to CV. Then I will have 80 times 10 power of negative 6 equals to my capacitance times my voltage, which is 16. Okay, that would give me a capacitance of 5 times 10 power of negative 6 farads. That means it's actually the capacitance is equals to 5 microfarad, and that's the answer for the first part. Okay. After that, the next question goes, determine the potential difference across the capacitor if the charge on the plate is 240 microcoulomb. So now I have the same capacitor, right? I still have the same capacitor, but its potential difference is going to change. So that means I still have my capacitance. So again, I will have Q equals to CV. But this time, I have 240 times 10 power of negative 6 on the left hand side, and then I will have C to be from the result that we had before, which is 5 times 10 power of negative 6, and then my voltage is what I'm looking for. Okay, so simply put, it is just 240 over 5. 240 over 5, because the 10 power of negative 6 cancels out, and I'm left with 48 volts, and that's the final answer for the second part of problem 1. Okay, moving on to the second question. Here we have, so previously what we had was we relate between charge and voltage to capacitor. Now we have actual physical dimensions. Let's read the question. A parallel plate capacitor has plates of area 25 centimeter square with separation of distance 0.25 millimeters of air. The capacitor is connected to a 12 volt battery. Calculate the capacitance of the capacitor and the amount of charge stored in capacitor. So if you have air, in between plates, then what you're going to have is C equals to epsilon naught A over D as the capacitance, right? So I have epsilon naught. Epsilon naught is a constant. It is the permittivity of free space. It's going to be 8.85 times 10 power of negative 12. And then I have the area of the plates, which is 25 centimeters square, which is 25 times 10 power of negative 4, converted to meters. And then over the distance between the plates, which is 0.25 times 10 power of negative 3. Okay, so if you key that into your calculator, what you will find is that it is going to be 88.5 picofarad, which is equal to 88.5 times 10 power of negative 12 farads. Okay, let's do the second part of the question, which is the amount of charge stored in the capacitor, which brings us back to the equation before, which is Q equals to CV. This time I know what is my C, 88.5 times 10 power of negative 12, and then my voltage is 12, and now all I'm looking for is just Q, right? If you key that into your calculator, what you'll find is that you will have 1.062 nanocoulombs, which is 1.062 times 10 power of negative 9 coulombs. So those are your two answers 1.062, and 88.5 times 10 power of negative 12. Okay. Okay, moving on to problem 3. Let's look at the question. This is a question on dielectrics. Capacitor A has a capacitance of 3.2 nanofarads. Okay, so I have an initial capacitance of 3.2 nanofarads, and then when a dielectric material is placed between the plates, the capacitance increases to 8 nanofarads. So my final is 8 nanofarads. Okay, determine the dielectric constant of the dielectric material. So at this point we should remember that epsilon, or the relative permittivity, which is the dielectric constant, is simply equal to Cf over Ci, which is going to be 8 over 3.2. Okay, so this means that my relative permittivity is just 2.5. Again, relative permittivity is just a constant, right? It has no units. Okay, let's look at B. Calculate the permittivity of dielectric material. So if I were to find out the permittivity of the material, I simply need to multiply the relative permittivity to the permittivity of free space, which is epsilon naught. Okay, I just have to multiply them too. So then I have epsilon material equals to 2.5 times 8.85 times 10 power of negative 12. Okay, that's 2.5. Okay, so then what I'm left with is going to be 125 times 10 power of negative 12. This is the permittivity of the dielectric material. Okay, so let me just highlight the answers that I've had so far. I have 2.5, and then I have this value. Okay, 22.125 times 10 power of negative 12, and the unit that we should use is actually farads per meter. Should be okay. Okay, so I'm going to have farads per meter. Okay, this is B. Okay, now for C, there is actually two ways of doing it. You can use C equals to 3.2. So let's just write down the actual equation. You have C equals to epsilon A over D. So there's two ways of going about it. You can use Ci. Okay, then your epsilon will be epsilon naught A over D. Or you can use Cf, but then this one would be epsilon R, epsilon naught. Okay, or more specifically, I can just use the epsilon material. Yep, there we go. And then A over D. That's what you'll have. If you to proceed with the Ci, I will have 3.2 times 10 power of negative 9 is equal to 8.85 times 10 power of negative 12. The area is 20 times 10 power of negative 4, right, over D. That would give me my D to be 0.55 millimeters. Similarly, I can do the same for Cf. Okay, but this time, instead of using 8.85, I have 22.125. So it's going to be 22.125 times 10 power of negative 12. Area is still the same, 20 times 10 power of negative 4. Then over D, and this whole thing is equal to 8 nanofarads. So 8 times 10 power of negative 9. And again, this will give me the same answer, which is D is equals to 0.55 millimeters, or approximately. Okay, so two methods, same answer. Okay, all right. Okay, so moving on to question 4, we are asked about energy. All right, so a 5 nanofarad capacitor is connected to a 9-volt DC power supply. Determine the energy stored when the capacitor is fully charged. So just to remind you that the energy stored in a capacitor is just half CV square, right, for this particular case. So then I'm going to have half, my capacitance is 5 times 10 power of negative nano is 9, and then voltage is just 9 square, right? So then I will have 202.5 nanojoule. So that's the amount of energy that is stored in this capacitor. Okay, so this is another way of asking about energy, right? Instead of giving, so in the previous question we had C and V, right? I can just write down that equation here, U equals to half CV square. But this time they gave us Q and C. So I just want to remind you that Q is equals to CV. That means V is equals to Q over C. So if I can substitute that into this equation, I'm going to have half C Q square C square, right? So then I'm left with half C, sorry. So I'm left with, let's see, Q square over C, all right? So then I can substitute the values. I will have half, and then Q square is 40 times 10 power of negative 6 squared divided by 8 nano, which is 8 times 10 power of negative 9, all right? And that gives me U equals to 0.1 joule, right? And that would be my final answer. Oh, that's not very nice, is it? Joule, there we go. Okay, and that sums up our video on the first part for capacitor. In the next video, I'm going to talk about capacitors in different combinations. So first we'll focus on series, and then parallel, and then combinations of that. Okay, all right, thank you very much.